could transmit it. In other words, it's light that comes out in some way, shape, or form, right? That vibrations are restricted to a single plane, not just in phase. That is a common mistake. That is a mistake I have made in the past too. It's not just in phase. It is restricted to a single plane. What I mean by that, and this picture down here will help with this idea here. And we'll get to Polaroids here, Polarizers in a second. But light comes in and it's able to oscillate. You know, think of waves oscillating. It's able to oscillate in all different directions. So that's one with light oscillate with light waves oscillating in all different directions. Okay, unpolarized light, all different planes. If you need to think about this in angles, right? You got straight up and down at 90 degrees, right? Flat at 0, you know, between the 0 and the 180 mark, and then you have the in between that, the in between there, right? All these different pieces of the circle where it's oscillating between. Polarized means you cut all of it out except one. Cut all of it out except one. Okay. So what's coming out after this first polarizer here? This would be vertically polarized light. It's only oscillating in one plane. Does everyone get that? It's only oscillating in one plane. Yes, it has. All right, now, kind of. Yes, it has no width. We'll just say, right? Otherwise, we're talking about this light path width.
Yeah,
and that's you know, an interesting little rabbit hole to chase. Yes, sir. To get out.
Like what does polarized light look like visually?
What does it look like visually to you? It's just light. It's all the same. It doesn't have any other effect. We'll get to some pretty cool effects.
So polarized light energy, right?
Here in a second. Yeah. Now, do I want to talk about Brewster's law yet? Yes, Brewster's law. Now, we're going to go through Brewster's, and then I'll go to Mouth's. Now, Brewster's. Brewster's law states this. I have a surface. All right, I have a surface, and depending upon the refractive indexes of the surface, right, light comes in. So let's just take, I don't know, say water, for example, because this is always a great example, because you've all seen this before. So the sun on the beach is starting to set, right? It's starting to set. Light comes from the sun, right? Hits some angle theta and reflects back up into, you know, your eyes, right? There. You know, and it reflects back up into your eyes, right? That's just standard reflection off the ocean. Now, at a very specific angle theta, all of the light that is reflected, all of it, is plane polarized. Plane polarized. I'm sorry. Those two angles should be the same, right, guys? Yeah. Yes. Reflected, right? Yes. Okay, they use a different one. Whatever. It's theta. It's an angle. Okay, this is referring to Brewster. If you want me to put a little b after it, I will. Yeah. Okay. We're good. Right. So some angle, right? At that specific angle, all the light is plane polarized. What I mean by that, let me come back to this picture right here. Here's a vertically polarized light. Right, here's vertically polarized light. Plane polarized would mean, and I really am not going to be able to draw this, right? But light comes in and hits coming from, you know, all sorts of different, like I said, I can't draw that. But whenever it comes up off the plane, it is oscillating back and forth parallel to the plane. That's the idea, plane polarized. Okay, not vertical at that time, plane polarized, parallel to the plane. Okay. Here, now, interesting phenomenon happens here. The portion that is, this is reflected, here is refracted, okay? The portion that is refracted is 90 degrees, at Brewster's angle, is exactly 90 degrees from the reflected ray. Exactly 90 degrees from the reflected ray, okay? And theta here, angle theta, is governed by this equation. By the way, it's wrong in your book. Who could have figured? N2 over N1 equals tan, and they use 5. The book says N1 over N2. Okay, N2 over N1 is tan 5. Sorry?
How much is reflected and how much is refracted?
Depends upon it depends upon the surface itself. Depends upon the surface itself. Generally, Brewster's angle, you're going to have majority being reflected. You're going to have majority being reflected. Okay. This generally is occurring. Brewster's angle is generally occurring with all the pretty colors you see out on the water at this time. Okay, the polarized light, but there are some other cool effects to do with polarization. Okay. That we're not talking about here, but one of them is you look out over the ocean, right, and you get this really bright glare coming off the ocean. You know what I'm talking about? A really, really bright glare at that time. And the glare a lot of times mixed with all sorts of pretty colors, too. Whenever you get that really bright glare off the ocean, we're talking you're getting close to Earth. Okay. It also has to do with whenever you're getting a bright glare off the pavement or asphalt when driving, okay? During that time, you're about at Brewster's angle. Okay, glares are generally associated with flame polarized light. Yes.
So like does that mean like when you're driving down the road, like down the road, something's like a little puddle when you get up close to it, it's like you're not
Yes, and my answer is possible. I'd have to think about that a little bit more.
So what's happening here? The light that's going through the sonar, like normal light, hasn't been over the plane, right?
Correct.
So it comes down, and the reason why it polarizes is all the other ones just can't reflect in the same direction, so only the one is perfectly at an angle to reflect, right? So it's like you have a whole group of them, and only one of them is at the right angle to reflect off.
That's the. Go through this, it's going to fall apart. Okay. There are 2 possible surface explanations, and just off the top of my head, I'm not sure which one is correct, although I should be sure. One is what you just said. It's the component of the light that works, right? The one that already is flame polarized is the only one that can reflect. The other option, which you're going to read about later, is certain things actually twist the light, polarize the light itself. So all pieces that reflect off in a polarized manner. And if I had to guess off the top of my head, double it up again, I'd say option 2 is correct. All the light is being reflected instead. It's oscillation direction, if you will, is change to be in line.
That's kind of where I was going, is that if there are a number of planes and there's only one, and all the other ones participate except for one, then you'd be reducing the amplitude of the light by a factor of infinity, so you basically have no light being reflected off. So I guess it has to be the second one.
Yeah,
that's
and
really weird.
what you're saying right there is going to be yes, but no, it's not reduced by a factor of intensity. It's about components. We'll get to that. We'll get to that. What we could actually say. But yes, it's going to reflect. Cause all there is being affected to change. Also. It actually eliminates the light being reflected at Brewster's angle. Good. What we're going to get to that with mouses a little bit. Polarizers. McKinley? Read. N1 is the substance you're coming from. So let's go ahead and let's do this problem right here. N1 is going to be air, right? I mean, that's air has a refractive index of 1. Water has a refractive index of about 1.33. And so let's calculate theta here. Let's calculate theta. Theta is going to equal the tan inverse of 1.33 over 1. What's theta come out to? Please give it to me in degrees. .06. We'll go with 53.1 degrees. Right. That's Brewster's angle whenever it comes to water. Okay, whenever it comes to water, which, by the way, is pretty low on the horizon. If you start thinking about this as about 53, what does that leave that other angle to be? Good. 37 degrees. 37 degrees. If you start thinking about the sun, how much time it spends directly overhead versus setting in there and then going into all the atmosphere and everything else. But 37 degrees is relatively low on the horizon. Relatively low on the horizon. I'm sorry? The 57. 53. I'm on this. The 53, right? That's the Brewster's angle. Lots of times, though, we will talk about measured to the horizontal or measured to the horizon, like we did here, 37, because your brain just naturally has grown up working, measuring angles to the horizontal, the horizon, right? And how high, quote unquote, is the sun? You're talking about how high above the horizon, right? Whenever the sun is directly overhead, your brain doesn't think 0 degrees. Your brain thinks 90 degrees. Okay, so sometimes we'll talk about horizon scale. We'll plot that. All right. If this is 53 degrees right here, Brewster's angle, what is the refracted? Let's pull that over here. What is theta refracted? What is the angle that it's refracted at? Which, by the way, the angle that we deal with when refracted is always, think Snell's law here, is always measured to the what? Surface or normal? Always measured to the normal. So the angle I'm looking for now is here. Theta refracted. What's that angle? How'd you get it? 37? 53? No to both 37 and 53.
180 minus 90.
Oh, yes. Excuse me. How'd you get it?
180
minus 9. Right? 180 minus 90 minus 53 gives me 37 degrees, which sets up an interesting here, right? Measures the horizontal is the same as the refracted, right? Right? The angle reflected measured to the horizontal is the same as the refracted, right? So by definition, because of Brewster's law, that those two, the reflected and the refracted, have to be 90 degrees to each other. Emily, then Mitchell.
Wait, so were we saying that was theta refract or refract?
All right. Right, so far, we have dealt with this nice little naive world where light either refracts or reflects, and there is no choice. That's not true, right? Light generally does both. Some surfaces are very reflective, some aren't reflective at all. They don't scatter light unless it penetrates and refract. Think of water right now. Think of water. You can see reflections off of water, right? You can see reflections off of water. That's the reflect part. You can also see down into the water, right? That's the refract part. You can get both going on. So parts, components of the light, if you will, reflect, and components of the light refract.
I was asking which one we're measuring. Which one were we saying the final, like 37 for?
This would be if you were asked about I'm combining reflected and refracted into one word. The refracted ray, okay? If you were asked, so here's the refracted ray. If you were asked about what is the reflected ray or what is Brewster's angle, Brewster's angle.
Wait, so then is the other one 53, the red one?
Yes. This is 53. This is 53. This would be 37.
Okay, that's us. So you're...
We good? Okay, another problem. When looking at a piece of glass, certain angle, all of the light being reflected becomes plane polarized. What is the angle of reflection and refraction? I mean, this is the exact same idea. Why don't you do that right now yourself? Go. Sorry, keep going if you need to. Now, here, this was the exact same problem. What was Brewster's angle, please? 56? 56 degrees. And what was the reflected? Excuse me, the refracted here. What was the refracted ray? 34 degrees. 33.7, 34 degrees. By the way, you can also figure out what substance it is. This is another type of problem that we haven't dealt with. That you can figure out what substance you're dealing with. You know, if they tell you that light comes in, you know, here's whatever. All right, star coming in, light comes in, hits at Brewster's angle, right? Hits at Brewster's angle coming through air to start out with, and then they tell you what Brewster's angle is, you know, they equals 32 degrees, and then they don't tell you anything else. You can figure out what the substance is, right? You can figure out what the substance is. Or you can work backwards. If they don't tell you this angle, you can work backwards using Snell's law, right? So if they tell you, let's say, this angle, 4 degrees. So work backwards here. Work backwards. Okay? Heck, you don't even need to know angle. You always use system of equations, Snell's law and Brewster's together. Never mind that, we'll get to that later. Short on time, mouse. All right, now, what you have right there are polarizers. Oh boy. Okay, our polarizers. Now, everybody has one. Hold them up to the light. And look through them. There's the light too long, right? Look through them. It cuts the intensity of light down by about what percentage? 10. Yeah, about 50%. It about cuts the. If it's working ideally, it should cut the intensity of light down about in half. Okay, about in half. Okay. Now, here's what I want you to do. You're going to have to share with a friend. Now, you take your friend, and then your friend takes both of them back. All right. So I want you to take the two polarizers. I'm going to borrow yours. You're going to take the two polarizers, and you're going to stack them. And you're going to stack them, and then you're going to try to look through them. Right. Compare it together to one of them by themselves. Then I want you to, with them together, rotate slowly 90 degrees. Take them together, see what it's like, and then twisting only one of them, rotate it slowly 90 degrees. All right?
Please turn. I didn't do that.
Those games.
All right, now what's happening? You got two polarizers. The first polarizer is something like this. Here's the general setup. Let's go to the rope idea of a wave on a rope, okay? And then a pallet, right? Slots with wood frames between, okay? So here's the idea. Now, whenever you have, by the way, all a polarizer is it's dark with slits in it that lets the light go through, right? The light can only go through slits here, all right? That's the only way it gets through. Rope can go through, if you have your two polarizers turned like this, the rope can get through both of them. Does that make sense? But if you have one turned vertical and one turned sideways, the rope gets through the first one, but is blocked by the second one. Yeah?
That are small enough to only left and right as infinitely.
It's more complex than that, but the answer is now infinitely thin. You're letting through only a very short, you're letting through a very small, precise, if you will, component of that. In other words, it's so close that it's polarized that we call it polarized. Now, here's the thing you need to realize. Whenever it goes through the first slit, or excuse me, not the first slit, the first polarizer, the light is cut in half. The first one cuts the light down 50%, right then and there. Okay? 50% right then and there. The second one then lowers the percentage of light less than that or keeps it at 50%. If it's a line at a 0 degree angle, right, we're both pointing the exact same way, you will find that the same amount of light comes through, 50%. Okay? On the other hand, whenever you were turning these guys, it wasn't like a linear effect. It was like light, kind of getting dark, and then all of a sudden it got really dark, right? As you continue to go. The equation that tells you how much light comes through the second guy is that I equals I naught cosine theta. Now, let me point out, I naught, the initial intensity of light, is always going to be 50%. 50% the original. Okay, it'll always be 50% of the original. Okay, and then as your angle grows to 90%, you'll get where no light is transmitted. You'll get where no light is transmitted. Can
The reason you can see like electronic flash with polarized sunglasses, but you can't with regular.
Say that again?
The reason you cannot see the screen of an electronic flash with polarized sunglasses, but you can with regular.
All right, so let's talk about sunglasses. Sunglasses, polarizing glasses, are simply a set of these guys. Simply a set of these guys. They're polarizers. Okay. By the way, that these guys have names. Okay. These guys have names. The first guy, if you're dealing with a set of them, the first guy is called the polarizer. The second guy is called the analyzer. First guy is called the polarizer. Second guy is called the analyzer. Now. Sunglasses, just a couple of polarizers. That's it. With the slits turned vertical. With the slits turned vertical, okay? So the idea is glare that occurs is where light hits the plane and is reflected in a plane polarized manner, meaning the light is oscillating like this up at you. Well, light oscillating like this, slits vertical, light oscillating horizontal, if you will. The light can't make it through the polarizer. The only light that is allowed to come through is the vertical. Okay? The vertical. Which is why with sunglasses you can see the surrounding world, right? You can see the surrounding world, but you don't see any glare anymore. You don't see any glare anymore. Electronic devices, not sure, I'd have to think about the way LCDs put out intensity of light, but I'd have to think about that a little bit more. Okay, but in a very similar fashion. Apparently the light is coming out of electronic devices that have been polarized in some way. If you took another pair of sunglasses and turned them, depending on how good the polarizers were, so I should say that to start out with, and you turned it 90 degrees, you can see, ideally, it's working, right? Make sure they're polarized sunglasses.
Yeah, so what are sunglasses that aren't polarized?
If they're not polarized, they're just tinted, right? They're just tinted. They try to darken. They try to cut down some of the light by absorbing it, right? Instead of letting it transmit. But if they're polarized, they don't just absorb. They get rid of it.
So if you
Only
took,
let
like,
one plane come through.
so if you took two sunglass lenses, put one this way and put them on top of each other, you would be able to see through.
If they were good polarizers. Now, let me also say this. This equation, this deals with the analyzer second. Remember, the initial intensity, I naught, will always be 50% whatever came out of the star, whatever came out of the sun, whatever came out of the flashlight, whatever. Okay, that's always 50% to start out with, and we're going to cut it that far from there. That I naught comes from not just one plane, but it comes from the components of every plane possible. Here's what I'm getting at. Let me try to draw this out. If I have a vertical, light comes like, oscillating at all different angles. So let me give you a few. Now imagine light starting where you are and going into the void. So I got some oscillating like this, some like this, some like this, some like that. And let's say my slits that I'm going to run it through are horizontal, right? Meaning that none of the vertical is going to get through. Well, this guy will make it through just fine, right? This guy will make it through just fine.
Teacher, pardon the interruption. We wanted to make
This
sure,
guy-
are the students taking the ACT prep?
This component and this component of these guys will make it through. Okay?
Here,